Hello everyone, today we're going to be talking about the current state of quantum computing. Now before we go into the current state of quantum computing, we sort of have to talk about what exactly is a quantum computer and what exactly is this whole thing. So first of all, a normal computer, like a normal desktop or whatever, would store information in bits, so these can either have the value of 0 or 1. But, however, a quantum computer, this stores information in something called qubits. So now these can be 0 and 1, and at every point between, all at the same time. This is using the theory of superposition, which we're not really going to go into because that's far beyond the scope of this video, but it's important to understand that. Alright, and then quantum computers are able to manipulate all the combinations of bits simultaneously because of the way qubits work. So that means that they can do many operations all at the same time. So they're far faster than a conventional computer. So, for example, a 30 qubit computer would have about 10 teraflops of computing power. And then, for comparison, the Intel Core i7-4770K has about 182 gigaflops of computing power. So you can see, just with 30 qubits, how much computing power you can get out of one of these. And then one other thing it uses is the theory of entanglement. So basically what this is that scientists could know the value of a qubit without actually looking or observing at them. Now this is just a basic overview of how quantum computing works because, the full thing is far beyond the scope of this video. Alright, and then here is a picture of an actual quantum computer developed by D-Wave Systems, and this would be the inside of it. And you can see this looks very different from a traditional computer, and we'll go into why a little later. So, where are we now? So it's still very limited. So there have been many breakthroughs over the years which have been advancing quantum computing, significantly, even if it's only in, not huge increments. But it is still a very far ways off from being practically implemented. So however, Microsoft does claim that they will have a working quantum computer within the next 10 years, which is pretty interesting news. And something interesting about this thing is that they would use a small quantum computer combined with a traditional computer. So then the traditional part would handle most day-to-day things, and the quantum computer component would tackle the most difficult tasks. So this would sort of be a hybrid computer, but it should get the power out of the quantum computer as well. Alright, now let's go into some important breakthroughs over the past several years. So in 2000, Los Alamos National Laboratory created a 7-bit quantum computer that used nuclear magnetic resonance to manipulate particles in a liquid. So basically what they did was that they had a quantum computer in one drop of liquid, and then they used this to sort of make the particles line up and turn into a sort of functional little computer. And then the same year, IBM also developed a 5-qubit computer which could be programmed by radio frequency pulses, and that's not a huge deal, but that's basically how they made stuff work. And then the cool thing about this was that they used it to find the period of a function. And what's significant about that was that a normal computer would have to do several steps in order to find the period of a function, but the quantum computer was able to do it all in one step, making it significantly faster. Then in 2001, IBM used a 7-qubit computer to find the prime factors of a number, which is a pretty important test, and that showed that they were getting more and more functionality. Then in 2005, the first qubit or 8-qubit quantum computer was developed, so that was showing that they were increasing in size. And then in 2007, D-Wave, which is a Canadian company that makes quantum computers, demonstrated a 16-qubit quantum computer. And then this one was able to solve puzzles like the Sudoku puzzle and other matching type problems. Now all those breakthroughs were not super recent, so let's move on to some more recent improvements in quantum computing. So IBM recently developed an actual physical chip that used qubits, and this was a very interesting thing. So what they did was that, or like what was so important about it, was that it became highly conductive when it was cooled to a very low temperature. So that was what allowed it to work. And then, although it was fairly simple, it was only 4 qubits in a 2x2 structure. This was a big breakthrough because previous designs had only had the qubits in a line, and this was the first time they were able to make it in a chip, which is more like what computers are today. And then this also fixed 2 errors that have been plaguing quantum computing, which would make qubits become distorted or switch to the wrong values, and then this chip was able to rectify those problems in many occasions, so that was a very important step. And then also, Google and UCSB built a 9-qubit array that, similarly to IBM's chip, prevented errors that occurred from so it didn't actually prevent errors, but what it did was, like, if any errors happened, it would be able to sort of get around them and prevent later calculations from being messed up by an earlier on error. And then this also showed that larger arrays of qubits would actually become more stable in some occasions. So that was very promising for making larger and larger quantum computers and getting closer and closer to them becoming a reality and practical. Alright, and then the researchers from the University of New South Wales were able to make a qubit chip in silicon. So basically what they did was they modified current gen silicon transistors from a normal computer and then used those to have qubits instead of bits. And then that was pretty cool because that could be a new way to tackle this problem and could make it more practical and happen sooner. And then there have been also more recent improvements lately. So this one is not directly about quantum computing, but it would help. So what happened was researchers observed the quantum Zeno effect for the first time. And basically what that is that it's been theorized that you could stop a particle's movement simply by observing it. And this was actually done for the first time very recently, so that was pretty big in the field of quantum physics. But basically how this relates to quantum computing technology is that it helped prove the theory of quantum cryptography. So basically an intruder couldn't, hack in and spy on what you're doing, because as soon as they start observing these particles moving, all the motion stops. So basically all the data transfer, all the activities going on it's just all frozen, so they'd have absolutely nothing to be looking at. Then the other cool thing is this could lead to something like a quantum sensor or a quantum switch that could react to some sort of stimuli or something happening almost instantaneously, because the second anything happened, this all stops. So yeah. Alright, and then Google, NASA, the University Space Research, and D-Wave signed an agreement that would allow Google, NASA, and University Space Research to gain access to the latest D-Wave machines as soon as they are available. So now, an important clarification here is D-Wave is one of the main manufacturers of actual physical quantum computing machines. So what this would allow to happen would be that these companies could be doing research on these quantum computers as soon as they were available, which would help greatly speed up research into quantum computing and help make them more and more refined and practical. Alright, and now the quantum computing has not been without many problems. So, first of all, different pieces needed to make a quantum computer have all been individually shown to work. Like, people have made qubits line up, or they've made a chip, or they've figured out some small little nuance, or figured out how to catch an error, but no one has ever really been close at all to putting all these pieces together. And that's what you would have to do to actually make one of these computers function. So until someone is able to do that, it's still a fair ways off. And another problem is most quantum computers right now operate at extremely cold temperatures. In fact, almost absolute zero. The reason for this is that most quantum computers use superconductors. A superconductor is a material that conducts electricity with zero resistance, but this only works below a certain temperature. So in the case of these quantum computers, that needs these to make the qubits and everything work properly, but they only work at a very, very cold temperature. So if we were to go back to the computer we were looking at earlier, that would explain this strange looking design, because the conditions it operates under are very different from the conditions any sort of traditional computer operates under. And this is not exactly practical, because you couldn't have, your home computer in some giant refrigeration box. So they'll have to either find some way to work around that or improve on that somehow. And then they're also extremely sensitive, so a very small disturbance could jostle up all the qubits, and then all the data is corrupted and ruined. But probably the biggest problem would be scalability, because right now people have only demonstrated fairly small systems. So basically, while they can make a 6-qubit system, they couldn't make a 600-qubit system. And that's really going to have to be worked around somehow in the future if they ever want to become practical, because people can't just keep making, this little 9-qubit system to do prime factors if they actually want to replace traditional computing. And then one other problem is that once the proof of concept has been done, there's no academic motivation to keep working on that. So basically, someone makes a 5-qubit computer to do a task. Now, there's no academic reason or motivation for someone to try to improve on that and keep working on that, because they're not going to get the same sort of recognition that the first person that did this will get. So that sort of leaves it in the hands of corporations. So it would have to be done with profit in mind, but the problem is that it is very expensive, time-consuming, and incredibly complicated to work on that. So the question is, if companies will keep working on this in the future and get it actually practical and working. Alright, so this has sort of been a overview of the basics of quantum computing, as well as a good examination on the current state of them. If you have any questions, feel free to leave them in the comments below. Thank you for watching. See you all next time.